Hi everyone, we are team G4T7 and today we'll be sharing our project on data structures on SMU SQL. This will be the table of contents. So in today's data-driven world, applications like online retail platforms and real-time analytics rely heavily on in-memory databases for fast data access and processing. Our project aims to simulate real-world database usage by running high volumes of SQL queries in different scenarios. Through this project, we seek to understand the efficiency of different data structures in handling such operations, focusing on speed and scalability. So this will be the structure of our SMU SQL. On layer 1 will be the database consisting of a hash map of table names to the table implementations. Layer 2 will be our table implementations, and layer 3 will be the rows, which are columns and values in a hash map. So we have 4 table implementations: array list, hash map, AVL tree, and red black tree. Our project emphasizes finding out the efficiency at the table layer, analyzing how the different data structures impacts the SQL operations. So for our first table implementation will be array list, which consists of columns, which are strings inside of the row, values, which are objects inside of a row, the primary key, which is the first column in a row, as well as a primary key map which stores the primary key and the value in the corresponding row. So the complexity for array list will be the following. O1 time for insert, as we can just directly add the row without iterating through the list, and for select, update, and delete will be O(n) time, as we have to iterate through all the rows checking the conditions. Our next implementation will be the hash map. Our hash map consists of rows, which are primary key for each row and a list of values representing each column's data, a list of strings which for each column in the table, a list of objects representing each row data where each object is the value, and the primary key, which is the first column value in each row. The complexity of hash map is given as follows. O1 time, as we can insert simply by hashing the primary key. Select for O1 direct retrieval of primary key, but O(n) for conditional select to iterate through all the rows to evaluate each condition. O1 time for updating and deleting if we are given the primary key to update and delete. However, O(n) for conditional update, as we will need to look through all the rows as well. Next will be the AVL tree. So our AVL tree consists of rows, columns, primary key, name, and primary key 3. So rows will be a map of primary key to an inner map of columns of values. Columns will be a list of column names. Primary key name will be the unique name for each row, as well as primary key tree, which stores the primary keys of each row in an AVL tree. The following complexity is given: O log n for insert, select, update, and delete. Insert due to the balancing of an insertion into the AVL tree. Selecting, as we need to find the primary key inside the AVL tree given a condition. Update, as we need to find and remove the primary key and add it to its new location. And delete, as we need to delete the primary key from the AVL tree. Lastly, will be red black tree. So red black tree consists of columns, which is a list of column names, primary key, which is the name of the primary key column, primary key map, which is a tree map of row objects, and column red black trees, which is a tree map of column tree maps where each column tree map stores a list of primary keys corresponding to a particular column value. Do note that in Java, tree map is represented as a red black tree, and hence we call it a red black tree. So the complexity are given as follows. For insert is O log n as primary key, as we can just add the primary key to each column tree map after finding its correct position. Select will be O log n, as we can find the primary keys in the column tree maps given the condition. Update O log n, as we remove the primary keys in the previous column tree map and add it to its new position given the condition. And delete, as we O log n, as well as we need to remove the primary key in the past column tree maps. Now we'll be moving on to our experiment. So our objective was to evaluate the efficiency of the different table implementations across different distributions of query types. So we have configured 4 different types of workloads consisting of 100,000 queries. The general case, which is an even distribution of all query types. Heavy select, which is a 75% of select and complex queries. heavy insert and delete, which is 75% insertion and deletion queries, as well as heavy update, which consists of 75% update and complex update queries. We will then calculate the mean time in seconds for each implementation to complete each workload. Now we will talk about the hypothesis for each case. So for workload 1, we believe that red black tree will be the fastest, followed by AVL tree, hashmap, and array list. This is because red black tree has the shortest time complexity in general, and array list is the slowest for every operation except for insert. Next will be heavy select. AVL tree will be the most efficient due to strict balancing, followed by red black tree for range traversal given the O log and time complexities. They will also have the shortest time complexity for select and complex select queries. Hashmap would still be faster than array list only for key-based lookups. For workload 3, heavy insert and delete, hashmap will be the fastest because of its O1 average time complexity, meaning it takes constant time regardless of the number of elements in the map. This is followed by red black trees, AVL trees, as they may trigger rotations to maintain tree balance. Array list is the worst because of the shifting of all subsequent elements to maintain the list order. Last will be heavy update. Red black tree will be the most efficient for update queries with minimal balancing required, followed by the AVL tree, both with O log and time complexity. The hashmap will still perform slightly better than array list for simple update queries, but both are still slower as of the ON time complexity. Now, here are the results for all our workloads. As you can see, AVL tree is the fastest for red heavy workloads, prioritizing search efficiency, followed by red black tree in write heavy scenarios due to the fewer rotations. Hashmap and array list lag behind, with hashmap being much slower for update queries, but still slightly better for the general case. So here are the analysis of our results. We found that AVL tree is much faster than red black tree in heavy select, as AVL trees prioritize read performance due to their strict balancing. This strict balance minimizes the path length from the root to the leaves and hence reduces search time. In converse, red black trees are much faster in AVL trees in heavy insert and delete, as red black trees are less strict in maintaining balance, leading to fewer rotations during such operations. Comparing array list and hashmap, we found that array list was much faster in hashmap in heavy update. Iterating through a hashmap can be slower due to the overhead of traversing buckets, especially if there are many collisions, which can result in slower performance as entries in the same bucket form a linked list-like structure. Now moving on to our X factor, we have some interesting insights. First insight is talking about memory locality versus complexity. So while hashmap can provide O1 complexity for direct access, array list can outperform them in some scenarios due to memory locality and lower iteration overhead, which could be slower due to collisions in the same bucket. This insight highlights that it is not simply about asymptotic complexity, but also about the memory access patterns and cache efficiency, where array list contiguous memory layout provides better cache performance. Next will be read versus write heavy workloads. Both self-balancing binary trees excel in different scenarios where AVL maintains stricter balance, leading to shorter path and faster search times, which makes it ideal for read heavy workloads where quick lookups are critical. But red black tree has a more relaxed balancing structure, allowing for faster insertions and deletions, which is more flexible for write heavy operations. Now we'll be sharing our reflections from this project. First is the possibility of misrepresentative conditional queries. Conditional queries in our experiment workloads may not always result in existing parameters being evaluated, resulting in the select, update, delete of no rows. This could lead to results that are misrepresentative of the nature of such queries. Next will be implementing suboptimal data structures. We recognize that our implementations of the aforementioned data structures are not perfect, and hence the results from the experiment may not be representative of an optimal implementation for each data structure, especially in real-world usage. Thank you.